Hello, good morning. Um, this lecture and Thursdays is going to be on the composite materials. And these are the carbon matrix composites. And they've been designed to improve thermal shock resistance and corrosion resistance. Two of the biggest problems in the refractory industry. So these are really superior materials. So I have three papers today I'd like to go over. The first one is thermomechanical characterization of magnesia carbon refractories by means of wedge splitting tests. And that's under controlled atmospheres as a function of temperature. So this paper is just taking the wedge splitting test and adapting it to high temperatures. So basically these carbon matrix composites have superior resistance to thermal shock. And this one I'm looking at today is an MgO carbon composite. That's the primary lining for a lot of steel vessels, especially the basic oxygen furnaces. And these materials have low thermal expansion and high thermal conductivity. Both of these characteristics give good thermal shock resistance. The problem with these carbon matrix composites is carbon oxidizes at high temperature. So usually it starts oxidizing at 600. By the time it hits 800 degrees C, the oxidation is pretty extensive, and you end up removing the carbon, and you end up with an MgO skeleton. So they're great in thermal shock and corrosion resistance, as long as you keep the oxygen away from the or CO2 away from the carbon. So in this work, they measured the fracture surface energy by wedge splitting under a controlled atmosphere at elevated temperatures. So this was the chemistry of the material that was looked at. It's about a 96% MgO material. So this is the chemistry of the oxide. And then the loss on ignition indicated there was 13% carbon present. So that's as delivered. And the carbon is usually a combination of flake graphite and the resin, which is usually a phenolic resin. So this is after the wedge splitting test, and that was at 1500 degrees C. And the chemistry is the same for the oxide components, but the loss on ignition is a little bit lower, 10%. So testing at 1500 degrees C is basically coking the material. You're pyrolyzing the phenolic resin binder. So there's a little bit less carbon present during this because of the pyrolysis of the resin. The phenolic resin usually has about a 50% carbon yield. So there's usually 5–6% resin in these materials. So it lost about 3% during the pyrolysis process. So my guess is there's 3% amorphous carbon from the phenolic resin and about 7% flake graphite in this material. So this is again, this is the wedge splitting test. You have to put a notch in this material. You put these transmission pieces in that notch. You have two rollers, and then the wedge forces the rollers apart and causes the crack to move downward. So there's a vertical force, and then the wedge creates these two horizontal forces. So this test promotes stable crack propagation in these coarse grain refractories. The fracture area is pretty high. It's, after you take into account the notches, it's 65 by 65 millimeters. So this is 65 millimeters this way, and counting for the notch, it's 65 millimeters in that direction. And the overall sample size is 100 by 100 by 75 millimeters. So when you run a load displacement test on this type of setup, there are a couple examples here. This is the MgO carbon composite. This is an MgO chrome material. So you can see the MgO chrome material is stronger. It's a higher peak on the load. It's more linear, but then it has a pretty abrupt failure. So it's much more brittle than the MgO carbon composite. So the MgO carbon material has a lower load. It's more nonlinear. It's a less brittle, more ductile material. And the area under this low deflection curve is going to be higher. It takes more energy to propagate a crack in these materials. So again, this formula for the fracture surface energy, GF, is just 1 over the area, and it's the integral over the force displacement curve. So F delta, D delta. F is the horizontal force, delta is the horizontal displacement. So F is this horizontal force. So at room temperature, to get the horizontal displacement, you just use a displacement transducer that monitors the crack opening. Obviously, you can't do that at high temperatures because the transducer is not suitable for use at high temperatures. So in this work, for the elevated temperature test, the wedge sample is put in a furnace. On opposite faces of this furnace, there are windows, high temperature windows, most likely a fused silicon material that's transparent or a sapphire single crystal alumina that's transparent. You have to control the atmosphere. So it has to be a non-oxidizing atmosphere like nitrogen or argon. You don't want to oxidize the carbon. And then you can get that horizontal displacement from an optical dilatometer. So that can monitor the crack opening as you load the material. So in this work at the lower temperatures, they use the halogen lamp that illuminates the sample and it casts a shadow. The sample casts a shadow against the light source, and they have a high resolution camera that records the movement of the shadow. Then when you go to higher temperatures where there's enough radiation to see the sample, you don't need the halogen lamp, and you use the radiation of the sample to record the displacement again with a high resolution camera. So at the lower temperatures, and probably temperatures less than about 1100 degrees C, the halogen lamp illuminates the sample, and the shadow that's cast is recorded by a high resolution camera. So you can see the loading wedge here, the cylinders, the transmission wedges, and then the notch. So as a function of as the load is applied, as a function of the load, you can get the displacement, the crack opening displacement. Then at higher temperatures, greater than 1400 degrees C, you don't need the halogen lamp. There's enough heat radiation to see the setup. So this is what you see at higher temperatures. Again, you can see the wedge now, and then the cylinders, and then the transmission wedges, and then the crack. So you can monitor the delta, the crack displacement as you load it. And this is just what the sample looks like at high temperatures, looking through one of the windows in the furnace. So it's a circular window. This is 1200 degrees C under argon. So you can see the wedge, the cylinders, the transmission wedges, and then the notch here. You can actually see a crack that's been propagated from this starter notch. So they show a typical load displacement curve. This is at 1400 degrees C for that MgO carbon material. This one is fairly strong. It tends to be nonlinear here. Then you have this gradual failure with displacement. So using the area under this curve, they calculated the work of fracture as 146 joules per meter squared. So I just showed you this test method, the wedge splitting technique, how it can be used at elevated temperatures for these carbon-based materials. So they measure fracture surface energy by wedge splitting under controlled atmosphere up to 1500 degrees C. And we talked a little bit about the pyrolysis of the phenolic resin. Well, if you pre-coat the sample, you can pyrolyze the resin and then you won't have any loss on ignition during the testing. So you can do the same type of testing for a worker fracture, the chevron notch type sample, but you're also going to need a furnace with a controlled environment. So I have two other papers today. One shows the influence of the graphite content on the thermal shock. The other one is going to show the influence of the particle size distribution of the oxide. So this one is mechanical behavior and thermal shock, resistance of MgO carbon refractories, and we're going to look at the influence of the graphite content. This is a relatively new paper, 2017. So the thermal shock resistance of an MgO carbon refractory was investigated at different flake graphite contents. They used the wedge splitting test to get the fracture surface energy. And then they did some fractography to characterize the crack propagation paths. And then the thermal shock resistance was correlated to this fracture surface energy that's measured by the wedge splitting test. So there were several specimens here as a function of graphite content. This is the formula. They have fused magnesite. Of course, they're aggregates, then a finer magnesia powder. So the aggregates were kept constant at 70%. The magnesia powder decreased from left to right, and then the flake graphite content replaced a magnesia powder. So we're always looking at 27 weight percent combination of magnesia powder and graphite. So SG1 has 1% graphite and 26% magnesia powder. And then we'll get up to SG14, that's 14% graphite. And then the magnesia powder is reduced to 13%. So 1, 5, 10, and 14% were the flake graphite contents. There was 1% silicon metal added and 2% aluminum metal. So these are additives. These are anti-oxidation agents. They're basically oxygen getters. They're there to prevent oxidation of the carbon. Theoretically, they react with the oxygen present before it can react with the carbon. The phenolic resin, the powder plus the liquid portion was 5% in all of these. So when it's coked, there's probably about 2.5% residual carbon. So these powders were pressed. The resin was cured at 200 degrees C, and then they were coked at 1400 degrees C to pyrolyze the phenolic resin. So they measured bend strength and three-point bending, dynamic Young's modulus in resin by resonance technique. These were all both done on 25 by 25 by 140 millimeter bars. Thermal expansion was measured from room temperature to 1400 degrees C, and that has to be done in an inert atmosphere like nitrogen. These were 10 millimeter diameter by 50 millimeter long cylinders. And then the fracture surface energy was measured with the wedge splitting test with the normal size block, 75 by 100 by 100 millimeters. So again, this is the formula for the wedge splitting. GF is again the fracture surface energy, A is the area, F is the horizontal force, and delta is the horizontal displacement. So in this wedge splitting test, you get other information. You can get a notch tensile strength. So sigma NT is the notch tensile strength. That equals F maximum. So that's the maximum horizontal force. B and H are sample dimensions, the width and the height of the fracture area. And Y is the vertical distance from the center of gravity of the fracture area to the vertical force. And that's where the cylinders transmit the load to the wedges. So you can get a tensile strength. It's not a true tensile strength. It's called a notch tensile strength. It's not a pure tension. So you can get a strength from this test. You can also get what's called a characteristic length in the wedge splitting test. So LCH for L characteristic equals the fracture surface energy GF times the Young's elastic modulus, and that's divided by the strength, the notch tensile strength squared. So if we look at our R parameters, RST and R4 prime, RST was the fracture surface energy divided by the thermal expansion coefficient squared, and then the Young's modulus, and that's all to the 1/2 power. But R4 prime was the fracture surface energy times the elastic modulus divided by the fracture strength squared. That is this formula right here. So this characteristic length is basically R4 prime minus this term for Poisson's ratio, which contains Poisson's ratio. R4 prime was, if you remember, was derived in a triaxial stress state. That's why there's a Poisson effect in this equation. So basically, higher the R4 prime value, the better the thermal shock resistance. The higher this characteristic length, the better the thermal shock resistance. I'm not sure why they, well, I guess this is not a triaxial stress state. That's why this 1 minus 2 nu term is not needed. So LCH is very similar to R4 prime. The thermal shock was done on 25 by 25 by 140 millimeter bars. These bars were coked at 1400 degrees C before thermal shocking. So that pyrolyzes the resin. So the quenching temperature was 900. They were dropped into an oil bath, which was held at 20 degrees C. Each bar had 5 cycles, and then they measured the bend strength before and after cycling. This is just an X-ray diffraction diagram for SG1, G5, G10, and G14. and it's basically periclase and graphite. So the major peaks here, or the triangles and the stars, are periclase and graphite. And then at the highest temperatures, because we have some aluminum and silicon metal in these materials, you get a little bit of spinel forming, a little bit of aluminum nitride. It's coked under nitrogen. So there's some possibility of forming aluminum nitride and from the silicon metal and the carbon, silicon carbide. So there's trace amounts, the diamonds, the circle with the dot, and then the solid circle. You can see the peaks are just barely there. There's trace amounts of these other components. So when they looked at the microstructure, this is SG1. These are fracture surfaces. They're just pointing out these minor phases that are present. This is the spinel MgAl2O4. So there's some spinel forming on some of the MgO particles. And then this square is this photograph. So to higher magnification, this is 40 micron bar. This is a 5 micron bar. So you see these little flakes that are forming at high magnification. They did an EDS analysis on those, and it's basically aluminum and nitrogen. So these flakes are plate-like particles, or aluminum nitride particles that are forming from the aluminum metal. And basically, they're showing the same thing in SG5. So this area here, you see to the right. And again, you see these plate-like structures. So that's the aluminum nitride again, that's formed from the aluminum metal that's present. This is an SG10. And this more clearly shows the spinel particles. Again, spinel is MgAl2O4. These spinel particles are forming on the surfaces of a MgO particle. And then this is a 10 micron bar, so these are pretty high magnifications. You can also see some aluminum nitride platelets forming. And again, this is the EDS analysis showing that these plates are aluminum and nitrogen. And then the last one, SG14, again, they're showing areas of spinel. Here's an aluminum carbide area. It's pretty much in whisker form, aluminum carbide whisker. So again, the spinel is forming on magnesia particles. And here's some more aluminum nitride. This area here is blown up here. So you see these plate-like structures of aluminum nitride. So these micrographs are just pointing out the minor phases that are present. And when they run the wedge splitting test, this is the horizontal force versus the horizontal displacement. You have this nonlinear fracture behavior that becomes more nonlinear as the graphite content goes up. So this is SG1, SG5, SG10, and SG14. So the higher the carbon or graphite content, the lower the strength, but the bigger the area under these low displacement curves, and the more nonlinear the behavior becomes with higher graphite content. So SG1 is pretty linear. It's the most brittle. And then SG14 is the most ductile or the most nonlinear. So these curves really change as you increase the graphite content. So just looking at these curves, you would say going from G1 to G5 to G10 to G14, in that order, those should be more thermal shock resistant as you go up in graphite content. This is the notch tensile strength sigma NT from the wedge splitting test versus graphite content. and you can see the strength goes down. We saw that from the maximum in these curves here. So they get weaker with higher graphite content. This is the fracture surface energy versus graphite content. So the fracture surface energy from the wedge splitting test increases as you increase the graphite content. And that's because the area under these curves increases as you increase the graphite content. And then this is common, the fracture surface energy divided by the sigma NT, this notched tensile strength. So the fracture surface energy divided by the notched tensile strength, that ratio is shown here. So it's plotted against graphite content. So it increased with increasing graphite content. So the higher this ratio, the higher the ratio of the fracture surface energy to the tensile strength, the lower the brittleness, the higher the toughness, the better the thermal shock resistance. They also plotted the characteristic length from the wedge splitting test. And again, that increased with the increase in the graphite content. So the higher the LCH, the higher the characteristic length, the better the thermal shock resistance. And that's following R4 prime. They also calculated RST, and they showed that RST increased with increasing graphite content. So the better the value, the higher the value of RST, the better the thermal shock resistance. So all of these tests are showing that the material with the highest graphite content, 14%, should have the better thermal shock resistance compared to the material that is only 1% graphite. So this is the thermal shock test results. So you have room temperature bend strength before and after thermal shocking, and the residual strength ratio is also shown. So cold MOR before and after shocking. So the darker cross-hatched area is the cold MOR before thermal shocking, and then this lighter single line area is the cold MOR after thermal shocking. So you can see that the lower graphite material was stronger before thermal shocking, but actually the higher graphite material had a higher residual strength, just slightly higher than these other materials at lower graphite contents. So this is the residual strength ratio, this plot here. So the higher residual strength percentages are at the higher graphite contents. This trend, upward trend, is the same trend as with LCH, RST. So this material is a lot stronger to start out with. It has a fairly large strength loss during thermal shock. And then this material is weaker, but it is still stronger than this material, slightly stronger. So when you look at thermal shock behavior, this one lost the least amount of strength, so it has very good thermal shock resistance. The initial strength is not that important. It has to be strong enough for the application. So as long as this strength is sufficient to line let's say a BOF vessel, the burrs are strong enough, it doesn't really matter if it's weaker. What matters is that after thermal shock, it still retains most of its strength. that's still there in service. So this is the material. It's pretty gray in color. That's because of all the carbon present. You can barely see some of the MgO aggregates, the lighter areas. This is the crack that's propagated. So this is the sample after the wedge splitting test. This is a higher magnification of that crack that's growing. You can see there's some deviation from linear behavior. There's a MgO aggregate that went around. And then they modeled this. So they took an image of this crack, its crack path, and they used a fractal analysis of that crack image. And they got a fractal dimension D. So that fractal dimension D describes the behavior or nature of that crack path. So the higher the value of this fractal dimension D, the more tortuous the crack propagation path. So the higher the D value, the more tortuous the crack path, it should have higher thermal shock resistance, the higher work of fracture. So D increased with increasing graphite content. So that predicts better thermal shock resistance with increasing D. So this is that fractal dimension D versus graphite content, and it increases with graphite content, meaning that crack path is more tortuous. And the more tortuous the crack path, you do that by controlling the microstructure, the better the thermal shock resistance. So they looked at the crack propagation types. So you can have crack propagation within a grain, within an MgO grain. They label that CGG. You can have crack propagation between the grain and the matrix. They label that CGM. And you can have propagation of cracks in the matrix. That was CMM. So GG is in the grains, GM is at the interface, and MM is in the matrix. And then they looked at the length in the whole crack propagation path for each one of these types of crack propagation behaviors. So they had a capital L CGG, a capital L CGM, and a capital L CMM. So this was propagation within grains, propagations at the interface, and propagation in the matrix. And then they got a percentage here, the corresponding proportions of each one of these crack paths relative to the whole crack path. So small l is the portion of the crack that went through coarse grains. This small l GM is the portion of the cracks that went through the interface. And this small l MM is the portion of the crack that went through the matrix. So this is just the sum, capital L GG, capital L GM, capital L MM. So this is the total length of the crack. And then this is the length of the crack that was through the coarse grains. This is the length through the interface. And then this is the length through the matrix. So they were able to look at how this crack was moving through the material. So this is SG1, SG5, SG10, and SG14. And you can sort of see from these diagrams that the crack path is more tortuous in the G14 structure. So if it's green, you can see it's propagating across an MgO grain. If it's blue, it's the interface between the MgO grain and the matrix. And then if it's red, it's through the matrix. So they looked at these values here. The proportion in the coarse grains, the proportion in the interface, and the proportion in the matrix for all 5 of these. So the crack propagation path became more tortuous as the graphite content increased. So this is in the coarse grains. SG1, 6 or 7% of that crack path was through an MgO grain. But if you go across the higher graphite contents, it's down to 2.8%. And then through the interface, it starts out at 35% with the SG1, but as you go across this table to the higher graphite, it's now up to about 73%. So a totally different fracture path in the SG14 compared to the SG1. And then the matrix, it was 58% SG1 and it decreases to 24% in SG14. Then they made a ratio of the interface relative to the coarser grains. And that ratio increases from SG1 to SG14. So what is that telling you? In the high graphite content material, the interface is real important. So you can try to control the interfacial strength between the MgO grains and the carbon to improve the thermal shock resistance. So that's one of the key findings here, is that you want to control that strength, because that's the main crack propagation path. So if you have a very strong interfacial strength between the matrix and the MgO grains, that path is not going to be that active. If you have a weaker interface, that fracture path will be more active. So you want to control that interfacial strength. So the summaries of this experiment: increased graphite content, enhanced the irregularity of the crack propagation path. It made a more tortuous fracture path, and that improved the thermal shock resistance because of this more tortuous propagation path. As far as the test methods, as you increase the graphite content, you increase the nonlinear fracture behavior, you increase this ratio of the fracture surface energy to the tensile strength, you reduce the tensile strength, you increase the fracture surface energy, you increase this characteristic length LCH, which is basically R4 prime, and you increase the thermal shock damage parameter RST. So that was a study showing the effect of the graphite content on the thermal shock behavior. This other paper I picked shows the effect of particle grading on the fracture behavior and thermal shock resistance of these MgO carbon composites. This is a 2022 investigation. So they looked at the thermal shock resistance of an MgO carbon refractory with 2 different particle size distributions, basically a fine distribution and a coarse distribution. And they used the wedge splitting test to measure the mechanical behavior. But they also added a digital image of the fracture pattern, and they added acoustic emission. So they try to characterize in more detail the fracture behavior. And they correlated the thermal shock resistance to the fracture surface energy from the wedge splitting test. So they had 2 compositions, the C12 and an MC12. The C12 was the coarser distribution, the MC12 was the finer grain size distribution. They used fused magnesia. So this is a dense, low porosity magnesia at 3 different particle sizes, 3 to 1 millimeter, 1 to 0.2 millimeters, and 0.2 to 0 millimeters. The flake graphite was 100 mesh, They added an aluminum metal as an oxygen getter, an antioxidation agent. They also added B4C. That's also an antioxidation agent. It works a little differently than the metallic antioxidation agents. The B4C oxidizes and leaves a B2O3 glass, which coats the carbon and is a diffusion barrier. Obviously, if you create a glass, you lower some of the mechanical properties. So in a way, this is a good oxidation barrier, but it does lower the strength. And the resin was a phenolic resin, a powder and a liquid proportion at 4.5%. So clay graphite content was 12% constant. The antioxidation agents were constant, 3.75 for aluminum metal and 0.5 for boron carbide. But you can see this was 42% coarse, and this is down to 20. The medium size was 33. This is up to 38. And the fines here were about 8, and now they're 25. So C12 is much coarser than MC12. So these powders were pressed. The resin was set at 200 degrees C, and these materials were coated to pyrolyze the resin at either 1,000 or 1,400 degrees C. So C12 is coarse, MC12 is finer. They use a 3-point bend strength, typical bend bar size, 25 by 25, 140 millimeters. They measured Young's modulus by a resonance technique. Thermal expansion was measured up to 1,400 degrees C under nitrogen with these smaller cylinders, 10 millimeters by 50 millimeters long, 10 millimeters in diameter. And the fracture surface energy was by wedge splitting on the typical sample size. But they use a digital image correlation. So they monitor the initiation and propagation of the cracks on the surfaces of the wedge splitting block. And they also use acoustic emission, and that detects the crack location, the crack mode, and the damage evolution as the sample is loaded and as the crack propagates. And I'm just reviewing these equations again. This is the wedge splitting, fracture surface energy, GF, 1 over A, and the integral of F d delta. And F here emphasize that it is the horizontal force. So FV is the vertical force when you apply the force of that wedge. So F is calculated from FV, the vertical force, that's divided by 2 tangent of alpha over 2. Alpha is the wedge angle. So you measure the vertical force in the mechanical test machine, and then you calculate the horizontal force with this equation. And again, this is the notch tensile strength. F maximum, the maximum force. B and H are the sample dimensions. And Y is this vertical distance of the center of gravity of the fracture area to the application of the vertical force. And then again, LCH, the characteristic length, GF times E over gamma sigma NT squared. And that's basically your R4 prime parameter. These bars that were subjected to thermal shock were the ones that were coked at 1,400 degrees C. So the phenolic resin is pyrolyzed into carbon. Typical quenching conditions, 900 degrees C to an oil bath at 20 degrees C. Samples recycled 5 times, and then the bend strength was measured to monitor the damage. So C12, this is the X-ray diffraction at 200 degrees C curing and at 1400 degrees C coking. So you're going to have the MgO periclase and the graphite, the solid square and the solid diamond. So they're the major peaks present in after both curing conditions. The double circle is aluminum metal. That's only going to show up in the 200 degrees C curing, so that the aluminum metal is there. And then at higher temperatures, you're going to form some spinel and some aluminum nitride. So the star and the triangle are present in very small amounts. The boron carbide was too low a level to detect at the 200 degrees C curing. And then the MC12 is basically the same, primarily periclase and graphite at either curing temperature, some aluminum metal at 200 degrees C curing, and then you're going to get a little aluminum nitride and spinel at the 1400 degrees C curing. So they looked at the microstructures, and this is C12 at 200, at 1400, and also 1400 degrees C. You can see these spherical particles. Oh, that's the aluminum metal. And these plate-like structures are the flake graphite. There's some aluminum nitride whiskers that are starting to form here. This is 40 microns. This is higher magnification 5. And then this bar is 5. And then they're showing these little particles, spinel forming on top of the MgO particles. And pretty much the same thing for MC12 at 200, 1400, and 1400. You can see the flake graphite. There's some aluminum metallic spheres here. The aluminum nitride whiskers that have formed, the spinel that has formed, and this is just another micrograph of more spinel that's forming. These are identified with EDS, so these features you can see the chemistry and identify what they are. This is the force displacement curve, a typical curves for these materials. This is C12. The black curve here is C12 at 200. The blue curve is C12 at 1400. So as you go up in temperature, the strength decreases, but the material becomes less brittle, more ductile, and then these areas under these curves start to increase. So the nonlinear fracture behavior increased with increasing temperature. And the same behavior for MC12. The black is at 200 degrees C curing. The MC12 in blue is after 1400 degrees C curing. So at room temperature, these tend to be more brittle. And as the temperature increases, they become less brittle or more ductile. So the more ductile they become, the more strain they can take, and the better they can resist thermal shock. So this is the porosity and density. So AP is the apparent porosity, BD is the bulk density. This is the curing temperature, 200, and this is the other curing temperature, 1400 degrees C. So C12 and MC12, both 5.5%, 6% porosity at 200. And then the bulk density is basically the same, about 3, and that's grams per cubic centimeter. And then at 1400, the porosity, this is 10.5, this is 11, they're almost identical. and the bulk densities 2.88 and 2.87 are almost identical. So when you cure this from 200 to 1400, you pyrolyze the phenolic resin. You have let's say a 50% carbon yield, then you have a 50% loss on ignition of that resin. So the porosity goes up, air goes up from about 5 to 10, 6 to 11, and then the density drops from about 3 to 2.88 and about 3 to 2.87. So the pyrolysis step or the coking step increases the porosity and decreases the density. So these are the results from the wet splitting test. So the increase in heat treatment temperature from 200 to 1400 resulted in an improvement in the predicted thermal shock behavior. So GC12 at 200 and 1400 curing, MC12 at 200 and 1400 curing. This is your vertical force in newtons. This is your Young's elastic modulus in GPa. This is the horizontal force maximum in newtons. So the calculated tensile strength, megapascals, calculated fracture surface energy in joules per meter squared, and then your characteristic length in millimeters. So if we're looking at this tensile strength, it's much stronger at 200 than at 1400 degrees curing for both C12 and MC12. So it goes from, let's say, 7 and 7 at 1400, and this goes up to 13 and about 10 or 11 at 200. So they're stronger before they're coked, but then the fracture surface energy increases after coking. This one is a slight increase, but this one, the finer material, the finer aggregate material, this one almost doubles. So the fracture energy really goes up at the higher curing temperature for the finer aggregate size material. And then the characteristic length, it increases as you increase the curing temperature from 200 to 1400. This one's pretty modest, 86 to 110, but this one again almost doubles, 70 to 132. So what this is saying that this material, MC12, the finer grain size distribution, should have better thermal shock resistance. So this is the digital imaging. This is C12 at 200. This is C12 at 1400. And then the strain in the horizontal direction, EXX. So the strain is in this horizontal direction, and it's color coded. Going from blue to this orange or red color, it just means there's more strain. So this is the horizontal force at the peak, and then right after the peak, you can see the crack is starting to grow. This is 50% after the maximum load. You have crack propagation, and then this is down to 15% post-peak, 15% of the horizontal force, and you can see the crack. And that was at 200 degrees C. This is at 1400 degrees C. And you can see the crack path is kind of tortuous. It's not linear at all. And then this is the evolution of the crack in the MC12 material at 200 and 1400 degrees C. And again, here's the peak levels, and then here's where the crack starts to grow after the peak. And down to 15% load, you can see the crack patterns. So these digital images, you get the horizontal strains. So the higher the strain, the better the thermal shock resistance. The more strain the material can take under stress, the lower the amount of damage that takes place. So these are the samples, C12 and MC12 at the two different curing temperatures, 200 and 1400 degrees C. This is at 90% of the pre-peak load, 94% of pre-peak, at the peak, 94% post-peak, 84% post-peak, 50% post-peak, and then 15%. So if you start looking at these numbers, the strain, these are the strains. This is 1.29 times 10 to the minus 1. This is 1.12 times 10 to the minus 1. So these are pretty large strains post-peak on the samples cured at 1400 degrees C. The strain is a little bigger in the finer material. And then there's a lot less strain. This is 5.84 times 10 to the minus 2, 4.17 times 10 to the minus 2. These are for the 200 degree C cures. So coking the material at high temperatures increases the amount of strain to failure. So at the same time they were doing the digital imaging, they did acoustic emission. And this is vertical force versus vertical displacement. So force versus strain, basically, at 200, 1400 for C12. The acoustic peaks, each one of these vertical lines is an event that takes place. So when you propagate a crack through a coarse grain or a matrix interface, it makes a noise, you pick it up with acoustic emission. The higher the peak, the more energy involved in that crack and that crack movement. So each blue peak is a fracture. The higher the peak, the more energy is absorbed. And then the red is the cumulative energy, and the black is the wedge splitting test. So the black is a load displacement curve. So you can see the wedge splitting shape changes at 1400 degrees C relative to 200 degrees C. A lower peak, more ductile material, and a longer tail. This is about somewhere between 1.5 and 2 millimeter displacement. This is somewhere between 3 and 3.5. And then they did the same thing for MC12. Again, it's force versus displacement. The black is the wedge splitting. You can see that the 1400 degrees C is more ductile. The 200 degrees C is more brittle. You can see the acoustic events. And you can also see that all the way down this crack propagation after the peak, you still have all these events taking place, absorbing energy. So this height or frequency of these acoustic emissions, the height, you can correlate it to a fracture process. So on this curve are the peak frequency versus time during the wedge splitting test. So this first dotted line here in red, anything below that line is just background noise. And then this dotted line below that second dotted line in this region here between the two dotted lines, those acoustic emissions are characteristic of a crack propagating in the matrix. And then above this other line, the top red line, these peaks are characteristic of a crack propagating in a grain. So they can use acoustic emission not only to see how much fracture events are taking place, but the magnitude of those events. They can split it into fracture within a grain or fracture in the matrix. So they can get a percentage here, the cracks in the particles, capital P%, and the crack in the matrix, capital M%, and take the ratio of P over M. So cracks in the particles in this 200-degree curing for C12, it's 16%, and it's 83% in the matrix. Then when you go up to the higher temperature after it's coked, more particles are cracking and less fracture in the matrix. And then the MC12, the finer material, you're starting out with a 10% relative to 16, so there's less coarse particles fracturing in the finer material and more matrix fracturing. This is 89 relative to 83. And then at the higher temperature, 1400 degrees C coking, about 26% of the particles are fracturing, but it's still less than in the coarse material. And then 73% of the fractures are in the matrix, which is higher than in the coarser material. So when you look at the ratios, this is 19 at 200, this is 11, this is 60 at 1400, this is 35. So the lower this ratio, the less brittle the material is. So these ratios predict the MC12 is better in thermal shock. So finally, when they do the thermal shock testing, this is the cold MR before and after thermal shocking, and then the residual strength here in blue. So C12, coarser material, MC12, finer material. And actually, the finer material is stronger before thermal shock testing because the coarser material obviously has the coarser particles, which gives bigger flaws and lowers the strength. So MC12, better initial strength and more retained strength. It retains 75% of its strength after thermal shocking. C12 only retains 68%. But you can look at the difference here. After thermal shocking, it's what's really important. This strength is much higher, actually, than either one of these strengths before and after thermal shocking. So what we predicted, MC12 should be better, and it actually is in these thermal shock tests. So these are polished sections looking at the microstructure of C12 before and after thermal shocking. You really can't see it's difficult to see the matrix interface, the matrix coarse particle interface cracking, but it's there. But you can see all the cracks in the coarse aggregates after thermal shocking. And then the MC12, same thing here. Less fracture through the coarser particles. There's obviously less coarse particles, but it's more ductile. So there's more fracture at these interfaces and more fracture in the matrix than at these interfaces. Again, it's just difficult to see. And that fracture behavior showed up in the acoustic emission also. They measured the thermal expansion, C12 versus MC12. So the finer material is in red. So going to a finer grain size actually lowered the thermal expansion of the composite a little bit, which also enhances the thermal shock behavior. Any material that has a decreased thermal expansion will have better thermal shock behavior. So in this work for the microstructure, the NGO carbon refractories that were made with the finer particle size distribution. That was the MC12. They were less brittle than the refractories produced with the coarse particle size distribution. And the refractories produced with the finer particle size also exhibited a bigger strain under the various loading stages than the refractories with the coarse particle size distribution. So they can withstand greater strain. They're going to better resist thermal shock fracture. And then for the test methods, the refractories produced with the finer particle size distribution, they created more microcracks in the matrix and at the matrix particle interfaces, and it consumed more energy than the refractories produced with the coarse particle size distribution. So these composites that were made with the finer particle size distribution have also increased interfacial area because of the finer MgO particles that tended to reduce the stress concentrations, increase thermal shock resistance, and that was relative to the coarse particle size materials. So by changing the particle size distribution, it changed the fracture path, the fracture mode, to one that consumed more energy during fracture. It redirected the crack along the matrix particle interfaces and through the matrix. So those are our two investigations into these composite materials. And again, these composites are much more thermal shock resistant than the other materials that we've talked about, the basic refractories, the alumina silica, the zirconia, and so on. So I'll talk about some more of these on Thursday. We'll look at some other compositions that there may be an alumina and spinel addition, and we'll see how these other variations that were made to the microstructure affect the thermal shock. So again, thanks for listening in today, and I'll see you on Thursday, and have a good rest of your day. Thank you.